In the previous video, we looked at machine learning done at large scale and the set of concepts that underlined how to think about which algorithms are suitable for that divide and conquer approach. So let's start looking at one of the most popular libraries for machine learning at very large scale, where the algorithms have been designed to be operatable as shared nothing executions. And that is MLlib under the Spark umbrella. So while the Stanford paper that I was talking about in the previous video broke down the essence of ML algorithms into steps that are solvable using divide and conquer, their target was MapReduce as being the vehicle for that execution. And consequently, some of the first set of libraries that were built to be executable at big data scale was done in MapReduce. So one example of that library was a very popular add-on to Hadoop called as Mahout. So as the name suggests, it was meant to be a way to guide executions of ML, but the algorithms themselves were written in MapReduce. So it had the same properties as any other data engineering job written in MapReduce, which was the fact that it was very highly scalable without, without being susceptible to interim failures at any point in the cluster. But at the same time, the cost it had to pay for it was to do barrier synchronization on the disk. So all the data exchange, information exchange was happening through disks. And that was making it really, really slow, particularly for iterative ML algorithms, because each iteration would produce outputs which were being written to disk, and then it became hard to, have significant progress on large scale data. So Spark, being fundamentally optimized for memory usage and therefore speed, created the first of the attempts at making ML algorithms operable using as much of in-memory computations as possible, while still fundamentally adhering to the shared nothing architecture, shared nothing design. So the MLlib that we see now obviously evolved over a period of time, but the motivation was always the same, which was, can I build something much faster to execute at scale than traditional MapReduce? So that was the key breakthrough here. So much so that a few years ago, Mahout itself was finally reincarnated as a Spark MLlib based implementation. So that kind of closed the loop on that entire story. All right, what does MLlib provide? As the name suggests, it's a pre-built library of a few different things. One is first and foremost a shared nothing algorithm, shared nothing parallel algorithms for common types of ML activities like classification, regression, recommendation engines, clustering, pattern mining, etc. And for each of these, there were variants which were implemented like XGBoost and stuff like that. If I remember right, we can take a look at the documentation for that. Apart from that, Spark MLlib also had a pre-built big data ready data engineering utilities. So these became very useful for understanding data preparation at large scale, doing it without having to write custom code. So transformations obviously were there, so that allowed data sets to be morphed into other representations. Data preparation steps were there, which included things like quality, cleansing, etc. Pipeline construction was one of the critical topics, and we'll talk about that. And then finally, model selection and hyperparameter tuning. So these became standard out-of-the-box utilities, which made it very, very popular and easy to use as well at the same time. And fundamentally, the motivation for this came from scikit-learn, in the sense that almost any machine learning execution follows a pipeline approach. And the pipeline itself is a collection of multiple different transformations on the data, finally having an algorithm that learns some kind of a fitment of a representation on the data to produce further transformations, as an example. So, in a sense, given a data frame, the pipelines would effectively standardize on each operation type that can happen on top of it, such that at the end of every operation, you continue to have a data frame. And so this allows chaining of arbitrary number of steps or arbitrary number of transformations that need to happen to effectively produce a really complex pipeline which is hierarchically contained, as the case may be. So standard APIs, that was the main thing. And data frames is the same data frame concept that we saw when discussing about Spark SQL. So in a nutshell, ML was actually interoperable with SQL, and that was also one of the breakthroughs from a practical standpoint, right, by the Spark community, because SQL was anyway and is continuing to be the case of a popular mechanism of analyzing data at large scale, and to be able to now weave in a SQL-based data preparation capability along with ML in the same architecture, the same design, same syntax was quite made it quite easy to use. Okay, so apart from pipelines, I think the main set of concepts are about a transformer, an estimator, and the notion of a pipeline itself, right? So a transformer is one which takes a data frame and converts into another data frame. So basically it transforms a data frame. So the examples here would be the feature transformers, like for instance, being able to change a particular feature, like the standard ones would be something like creating a dictionary mapping for a set of categorical variables. So that would be an example. It wouldn't change the rest of the columns, but the fact that it changed one column is itself sufficient, right, to think about it as a transformation. Likewise, there are many more, like being able to do scalar functions, change the string to string length, right, as an example. So those are all standard Python functions. You can just embed that and create your own custom transformer as well. ML models themselves are transformers. In what way? You might ask. So think of a model as having learned a representation. So when it has learned a representation, and when you fit it onto when you apply it onto a input data frame, it effectively transforms that data frame into a target data frame, which is as a result of applying that representation on that input data. So in a sense, the model converts the input data into a target representation based on what it has learned about the properties of the columns. So that also is in the same sense of the word a transformer. An estimator, on the other hand, is an ML algorithm that can be fit onto a data frame to produce a transformer. The key part is here the fact that the algorithm is actually trying to learn a representation. So it's actually already coded up a representation. So think of it that way. Most algorithms are, in fact, almost all algorithms are already having coded representations of, coded versions of the representation that you're trying to fit a data set into. So when the algorithm is executed on a data frame, you're effectively trying to fit the data frame onto that representation that it's coded up. And in doing so, you would create a mapping effectively. And that mapping can then be applied against any input data frame to produce a transformer. So that's why an estimator is the actual implementation of a model, and it, when applied against a data frame, produces a transformer. So then that can be used for transforming data sets, data frames rather. So the good part was, by standardizing APIs, any and all estimators will be considered so if it implements the fit method or exposes the fit method. So that's how the chaining was also possible quite easily, and the pipelines could just get extended. What is a pipeline itself? It just chains multiple transformers and estimators to specify an ML workflow. It is itself an estimator, because at the end of the day, it would basically provide an encoding or provide a representation, right, which, albeit complex, but it's still a representation. So then a pipeline that's ready is a specification or a representation and should be applied against a data frame to provide a pipeline model. So that's what a pipeline does. And then the pipeline model is a transformer, which you can then apply against any input data set to get the final output or the final result. So fairly clean design, I would say. It just allows chaining, and I think that's the most important to keep in mind. And chaining is what allows you to build a lot of complexity that you might need for your practical applications. Few things to note. So first and foremost, pipelines are layering lots of different types of abstractions on top of each other. But the core abstraction is the fact that something is a transformer or an estimator, and you can just chain them all together, like transformer, and then estimator, which just applies on a data frame to get a transformer, etc. So which means at compile time, anything beyond checking whether something is a transformer or an estimator and these things are chained correctly becomes hard to do. So specifically, if a transformer is expecting data types of a certain type, like columns of a certain type, so those kinds of checks become like impossible because the pipeline compilation is not actually set up for that. The pipeline compilation is set up for enforcing the chain, right? The chain adheres to the semantics that it's supposed to have. So the runtime checks is what you would have to resort to, which means the process of debugging, in case you've got the wrong type or in case you've got the wrong chaining through of columns, that becomes a bit more tedious. But yeah, people who use the Python are used to this anyway, because by default they don't compile Python programs, and it becomes runtime debugging. Nevertheless, yeah. The other thing to keep in mind is that pipelines in general could be quite complex. So you might want to think about outputting the final estimator that's getting created by a pipeline as a stored object on disk or on shared storage, so that you can come back and look at it at a later point in time. We'll anyway take a look at some best practices of how you would go about it and why you would go about it. So when that discussion comes up, you'll see that storage and retrieval of pipelines is a critical topic. Nevertheless, it pays to actually store this away for not just retrieval, but also the fact that in case subsequent steps in that pipeline usage or the pipeline model usage goes wrong, then Spark allows, or rather you can trace it back to specific disk versions that you stored and then recreated. Okay. The third point to note is that most ML algorithms written for this interface, they collapse the set of input columns and dependent and independent variables into what's called as a vector assembler. The reason for doing that, my guess would be that it creates the standard interface, right? So just basically getting a vector as the input, and then you would then do your thing on top of it, as opposed to having variable length of columns, variable set of columns, etc. for each use case. So that vector, the concept of a vector, becomes important to create, and the vector assembler actually does it for you. So once you're ready with the set of columns that you are expected to use within the ML model, you call the vector assembler, and then it does its thing. Okay, there's a bunch of data preparation functions, and this is something that Spark really excels at, or MLlib excels at. And then if that's not sufficient, then you could write your own using estimators and transformer interfaces. So let's take a look at some specific data preparation functions, which could be quite handy when you write your own code. So first and foremost, feature extractors. These are really nifty utilities to get to specific encodings of the input data, such that you don't have to deal with the vagaries of the input data. So what I mean by that is, the input data could be laid out in any form, like for instance, you could have free form text and columns alternating between categorical and numerical, etc. But then if you use some of these feature extractors, then it helps you standardize on exactly what the input vectors should be, or at least the processed information from that input data would be, so that you can then use additional transformations as required to create a pipeline. So one of the most popular ones, of course, is word2vec, which is a word embedding creation function. One of the other functions is TF-IDF. TF stands for term frequency. IDF is inverse document frequency. Term frequency, as the name suggests, is basically just a count of terms that's there in a particular document. Inverse document frequency, on the other hand, talks about in how many documents in the corpus does that word occur. So think of TF-IDF as a scoring function. The score applies to each word in any document in a corpus of documents. The idea being that if the TF-IDF score is it's high, then a TF-IDF score for a word document combination is high. It means that the word is quite uniquely associated with that document, and vice versa, right? Because then you can use that as a critical information to surface search results when you're searching for words across a set of documents. Obviously, search like Google search is much more complex. It uses other algorithms like PageRank, but TF-IDF is like one of the most common ways in which you can cluster text together. Okay, feature hasher is another one. So as the name suggests, it helps you convert a feature from something like categorical to like a standard numerical representation, which preserves the one-to-one mapping. So feature transformers are a bunch of functions based on the nature of the input data and the type of work that you want to do on top of it. So let's say it's words, basically document text that you're dealing with. Obviously, word2vec is helpful for extraction, but then you still need to do processing on top of it to do things like singleton extraction, dual token extractions, etc. And then you apply your own logic around stemming, around removal of common nouns and stuff like that. Word processing is like just a bunch of functions that are available for doing all of this easily. Dimensionality reduction, like the name suggests, is exactly what you would imagine. PCA style techniques for allowing large scale data reductions to happen. Encoding functions are also available. One-hot encoder is, of course, one of the most popular. Dictionary build is another one. Few such encoders. Scaling functions are critical for certain types of normalization that you'd want to do before an ML algorithm is trained. There's a bunch of different types of scalars available out of the box, and you can choose what you want. We spoke about vector assembler earlier, and then finally missing data. There are out of the box functions to deal with it. Now you might choose to not deal with some of the missing data, obviously, but then the fact that you might want to do certain processing and then decide on missing data and how to deal with it is like a practical way to deal with this problem statement. Okay, feature selectors are again a very nifty set of tools, and we find ourselves doing it all the time when practicing as data scientists, which is once the preparation is done, once you've got a bunch of variables ready to go, you could choose to, of course, do dimensionality reduction, but then you don't have interpretability on the new axes that get created. Instead, if you end up going with feature selectors, they could help you filter out functions, they could help you with functions to filter out certain classes of features which are not having certain desired properties. Like, for instance, one of the properties could be that you want only variables that have potentially high explanatory power for a certain outcome, which means they play a critical role in that representation. So therefore, you want to weed out those variables which do not have that kind of a critical roles, which means, for instance, low variance variables. So for the most part, the variable values look the same, and so there isn't much that you can actually write on top of in that kind of a setting. So you could use one of these functions to emit out only those variables which have a high variance, and then that becomes the basis for you to build more. So that's one set of feature selectors that are possible. There are a bunch of other such feature selectors based on various kinds of logic. And last but not the least, it's got a set of pretty cool approximation algorithms, especially as it pertains to hashing. So one specific class of hashing is basically what's called as locality sensitive hashing. What this is about is to allow representations, or okay, let's put it simply, to a lot of data sets which look similar, to end up having hash values which are also similar. So in contrast, right, if you didn't have locality sensitive hash, if you just had hashing, the hash function by mathematical definition is taking a broader domain and creating a smaller range, right? It's the creation of a range of smaller size that makes it a hash function as opposed to some other transformation. And that hash function typically ends up doing a random mapping. Random meaning the output range values do not have any specific sanctity to the order in which they are assigned to the input domain values. So you can't really infer order or infer semantics of relationships between the hash value outputs because it's fundamentally doing a random generation. Whereas in locality sensitive hashing, points which are closer to each other in the domain also have hashed values which are closer to each other in the range. And this is very useful as a property to build more functions in that pipeline to be able to transform in a way that's adherent or that's aware of the interpoint distance, etc. So all of that becomes feasible. Finally, there's also a bunch of tooling available for things like automated model tuning and selection. So one gentle point here that I want to make is that the world of automated machine learning, or in short, AutoML, is something that's quite popular in the broader data science community, including at small scale but also at large scale. But the name is actually a misnomer. It's not automated machine learning really, and so the word AutoML has this connotation of almost all of ML is automated. Not really. What it really refers to is the fact that hyperparameter tuning is automated, and that's the most common interpretation that people have taken forward when they design AutoML capabilities into their data science workbench or data science platforms. So what does automated hyperparameter tuning mean? It means that first and foremost, you've got the input variables all prepared and ready, quality is assured and things like that. You've got a bunch of output variables, or maybe one output variable or an outcome that you want to optimize against. Like for instance, it could be classification accuracy, FN scores, etc. And you also have like a breadth of algorithms to choose between, but you're not able to make up your mind as to which one to choose. In that kind of a setting, AutoML is very useful to just iterate through all the models that are at your disposal in parallel in some cases, right? The parallelism comes down to whether you have a cluster of that size available to run all these explorations in parallel. Nevertheless, AutoML basically cycles through the options, and for each option it also cycles through the parameters, and the parameters are chosen from a grid. The grid is essential for bounding the extent to which the search needs to go to. Otherwise, the search could be unbounded because the parameter space is usually an infinite range. So once the parameter search is run and it comes down to like a specific recommendation of parameter values, along with the choice of the algorithm, it then goes and runs an experiment. Like same thing happens across multiple different parameters for the same algorithm, and then eventually also multiple algorithms with new parameter value spaces. So all in all, AutoML allows you to go from prepared data to the final output in terms of model using automation. So like what I just spoke about in Spark 2, there are two methods for AutoML invocation. One is something called as train validation split. The other one is called cross validator. In either case, you will need a parameter grid to search over, like is always the case with all AutoML approaches. And then of course, an evaluator to use to rank the performance of the model so that you can pick and choose the models in terms of hierarchy and then propagate that forward. Cross validator is, as you can imagine, a function that helps you do cross validation. So yeah, definitely something that's very useful. And this is similar to the concept that you would encounter with scikit-learn as well. The other automated tuning and selection process that's available is train validation split. So here, unlike cross validation, which actually repeatedly picks samples from the same bag, so that you can arrive at multiple different experiments based on different ways in which you seed the set of data that you hold as the holdout set, etc. In train validation split, it's just one iteration, and that one iteration is probably enough, provided the data is large, the data is distributed randomly, and the sampling effectiveness is representative of the underlying class distribution that you are classifying on top of. So basically, in other words, simpler words, for big data model training, you cannot go wrong with train validation split as your choice of AutoML. Firstly, because it's faster, and that matters because the scale is large, but also you might not face a significant drop in optimality. And the reason for that is there is enough data, and therefore there is enough representation of patterns on which you train against. Okay, just going to pause here and we continue from here to look at the specific tuning options.